Right. Hello, interwebs. Welcome to the Onco Data Podcast. I'm Mark Gramling, VP of Oncology at LARVOL. So we're recording a little bit off schedule today, but I was able to track down my good friend Darko to talk a little AI today. So I'm going to go ahead and put this up on the webs, as they say. So maybe to give a more proper introduction, I want to say thanks, Darko, for joining me off schedule. And Darko, if you could reintroduce yourself. And frankly, I didn't know this until recently. I think you have your own podcast, Artificial Intelligence with Darko. So maybe if you could introduce yourself and plug your wares, Darko, that would be a great place to start.
Thank you so much, Mark. It's always a pleasure to join you at your podcast, and super interesting to discuss various topics with you. I'm sure that today's podcast will be interesting for the audience as well. And yes, I started artificial intelligence with Darko a few months ago. So hopefully I will also have some interesting materials to share there with the audience. But for today, I'm really excited. Looking forward to chat with you on some very interesting topics.
That sounds good. So everybody check out Artificial Intelligence with Darko, as well as checking out Onco Data Podcast that you can on social. So maybe a place to sort of start out, not to turn this into an internal business conversation, but Darko and I work together on a lot of things based on the CLIN database and outcomes data. A lot of our digitized KM curves and what we can do with KM curves, outcomes data, hazard ratios, and what's can be gleaned from the public. So maybe if you could give us a quick update, what's next for our LARVOL and Darko relationship in pseudo IPD and network meta-analysis? Can put you on the spot.
Yeah, so it's a very interesting project that we started several months ago at LARVOL, and it's iterating quickly through more and more advanced versions. So the first version of pseudo IPD was special because we could take a huge amount, almost entire body of evidence in terms of survival curves in oncology randomized control trials and reconstruct them to the level of pseudo individual patient data while preserving the privacy of the data and everything, just keeping up with the good clinical practices at the same time, going deeply into the data science of working with survival curves. And that project was resulted in one of the largest data sets around survival data with pseudo individual patient data. Now, the second project was also very interesting related to that. But to fast forward, what we're doing right now, we're trying to enable users and potential customers, companies, to actually create not just one pooled curve from the pseudo IPD data. The previous feature was that users could also take a lot of different trials and create a pooled curve. So right now we're trying to enable users to, for example, create two pooled curves and calculate the hazard ratio between them. So each of the pooled curves could contain potentially a larger amount of trials. So it's like meta-analysis taken to a much larger scale, where we can now perform analysis with much more flexibility and potentially on the larger scale. So that's a super interesting project, and hope that it will be useful for the oncology research.
So it begs the question, can you, in creating multiple pooled curves, is the construct to take 10 trials that are related enough to where you can do a pooled curve for the control arm and then a secondary pooled curve for the intervention, and then create a hazard ratio between the two. It's almost too obvious a statement, but of course, pseudo IPD is new. But I presume that's a driving impetus. You guys are working on that in the background.
Yes, that's a driving angle. So it would potentially enable to create a pooled curve of interventions, which would otherwise not be able to be combined in the same analysis, and also potentially create a pooled curve of standard of care, for example, or some other form of control. When we think about it that way, it's also a very important step towards creating large-scale synthetic control arms. So this is the only way to take a large number of trials, which for some of them we have individual data, for some of them we don't. But if we use the angle of synthetic reconstructed data, we can now combine them together and create, let's say, a 20 trial large synthetic control arm, and also 20 or 30 trial large intervention arm or multiple arms. So it's going towards large scale, the power of large scale, enabling what we couldn't do before. So we lose the randomization in a way, but with the scale and synthetic data, with the accuracy of synthetic data, we try to go for the angles that previously were not possible.
Fair enough. Well, to switch gears, that sounded a bit like a pitch for new CLIN features, which keep an eye on those for LARVOL CLIN. Darko will be working with our AI team on that. Completely switching topics for a second, and we'll keep it brief because this is the world's shortest podcast. I was cruising around your LinkedIn the other day while we were trying to schedule, and I saw that you've worked on, projects around predicting surface peptides or neoantigens in cancer. Now, the reason I wanted to ask you about it is I'm once upon a time was a cell biologist, but now I've been working in software for years. So I can picture on the largest construct LLM models what they do, assembling information. And also with projects that I've worked on with LARVOL and with you, in terms of outcomes prediction based on our data set, our extracted data set, how you do outcomes prediction or how you do curve extension, how you do hazard ratio prediction based on tumor type, MOA, and subsets. But even as a former cell biologist, I have a hard time where AI can predict surface antigen associated peptides. So I'm putting you on the spot again, Darko, the 2-minute version, or perhaps 90-second version of how that works, because it's harder for me to picture, even though I use AI on a daily basis. What would you say? Or as I like to tell my team, explain it to me like I'm 4 years old.
It's a good point. So it is definitely a field that is super interesting in oncology, and the oncology community in general had a lot of back and forth with these neoantigens and what they mean for the oncology research. Just for our audience, a very short intro to neoantigens. These are the molecules that are created in tumor cells, specifically because specific changes may occur in the molecules of tumor cells, in the sequences of those molecules, and then these changes actually may cause abnormalities in cell growth and other biochemical features of the cells. Now, why they're interesting? Because once this sequence is changed into a novel molecule that is now not the part of the healthy repertoire of sequences in healthy cells, we call it like the novel molecule, the novel antigen, the neoantigen. So these neoantigens are super interesting because for majority, if not all, tumor treatments, one of the largest problems is the side effects that originate from the fact that most treatments target tumor cells, but they also target the healthy cells, and side effects can be so limiting that they can limit the treatment effect. They can cause dramatic and drastic problems for patients. So having molecules that are specifically on tumor cells is super interesting for oncology research. And that's where the neoantigens come in. So I created this side project some time ago, which later I collaborated with a company called Oanalytica to develop an AI model called Onco Neo 400, which can predict whether a human organism, the immune system, will react to these neoantigens, but in a specific way, only if those neoantigens are on the surface of the cell. So that's interesting. A lot of neoantigens, they're inside the cell, so they're not accessible for many treatments in oncology. However, if they're on the surface of the cell, we developed an AI model that can predict accurately if the immune system will have recognition and reaction towards those neoantigens. Of course, it's a starting point towards developing this in different angles, but that's the core principle. As a lot of experimental data is now available in this field, we thought that we could use that data and train an AI model to predict that as accurately as possible.
Well, I may have been misinterpreted. So is it predicting immune cell response, or is it predicting even peptide sequences of neoantigens? Because I think I was thinking about the latter and not the former. So
Yes.
is it both or one of the two?
Yes, the latter. I think you're right.
Okay.
It's the latter. So neoantigens are extremely difficult, and it's in line with what you said. They're extremely difficult to predict in terms of whether they will appear on the surface of cell. So when they appear, then they're called the neoepitopes for our audience, but it's very difficult to predict that. So what's super interesting is that if they appear on the surface of the cell, then in many scenarios, they may become a viable targets for precision oncology, for that oncology that will focus on minimizing the targeting of any healthy cells in the organism.
Well, I said explain it to me like I'm 4 years old. That seems slightly elevated than 4 years old. But I'm going to have to leave it be because I only got 2 minutes left. So I'm going to switch gears. So I've been seeing a lot of this terminology about AGI versus ASI in artificial intelligence. And I guess I was seeing some of it reference in sort of the context of ChatGPT. I don't know if it's 4 or 4.5 and Llama passing the Turing test as reported. I think it was like the most strict Turing test earlier this year. It might have been March or April. I don't know if the publication's out. Those are vaguely associated concepts. But since I'm seeing AGI versus ASI, which is artificial superintelligence, I'm going to put you on the spot for the final time and say, how do you differentiate the two in exactly 1 minute? Darko, go.
Okay, in exactly 1 minute. So AGI would have very similar level of intelligence across all tasks that a human can do. So that would be a very quick definition. Like if we imagine everything that human can do cognitively with our brain, the AGI would approximately have the same ability. It would have the ability to switch between those domains, but it would be a very similar level to human level. Now the ACI, the artificial superintelligence, would overcome the human level, but not just overcome it in 10% better or 20% better. It would drastically overcome the human capabilities in almost all tasks. So we can just to be very intuitive, we could say 10x, 5x, 20x, but it would be a drastic difference compared to what a human can do in any of the cognitive fields, in any type of intelligence, whether it's the logical intelligence, mathematical, conversational, linguistic, emotional intelligence, artistic intelligence, musical intelligence. But if we imagine that on a much, much larger scale, much, much bigger capabilities than humans, that would be the ACI. Not sure if it was 1 minute, maybe it was 2, but hope.
I lost track. I lost track of my timer here on my desk, so we'll close enough. So we'll definitely leave that there. It's intimidating to think about AI in the broadest of terms. So maybe and I guess both of us will go back to focusing on AI and how it can help us develop treatments, improve treatments, predict outcomes in cancer, as we tend to focus on a day-to-day basis. So we'll leave it there. Make sure you check out clin.larvol.com, and follow us on social media, and maybe keep an eye out for Artificial Intelligence with Darko if you're interested in these type of topics and maybe want to get more in depth. So thanks everybody for listening. Thank you, Darko, as always. You're my top guest by volume, and it's not even close. So thanks again, Darko.
Thank you so much, Mark. It's really a pleasure to join you always, and hope that there will be a chance in the future also. And I want to thank all the everyone from the audience for joining us, and hope that it was an interesting story.
Absolutely. I'm sure I'll see you soon here, and I'm sure I'll see you soon in other contexts since we work together. Thank you, Darko. Thanks everyone for listening. Cheers.
Thank you so much.